isometries of a Riemannian manifold. It's a Lie group.
Kobayashi no Mizu. Pardon?
Kobayashi doesn't do.
You sure?
Yeah, he uses a more general result about actions of topological groups locally compact. He uses this general. The action must be effective, something like this, and he proves that in the case of the isometric group is effective by definition.
Yes, yes.
It's locally compact. This is what he proved.
He doesn't prove it's a Lie group? Or he quotes another theorem?
It's a Lie group because of this more general result
Ah.
that he only states.
Okay.
It's
I didn't realize that. Yeah, I think there was something I mentioned maybe that topological group that's locally compact and finite dimensional is a Lie group, something like this. Yes. Right.
Studies a lot of actions.
No, okay, so for a Lie group it's much more elementary. I tried to find a reference. Somehow I thought it was Kobayashi no Mizu. I see. Okay, I'll try to find one.
Helgason does that argument that it is locally compact. Helgason.
He also proves that.
But he doesn't prove more than continuous information group locally compact.
He doesn't prove it's a Lie group. He doesn't prove it's a Lie group either. Wow. How can you... Pardon? I think so. How can you do a book on symmetry space without proving the isometric group is a Lie group? That's weird. As everyone knows. Easy way out. Okay. So let me just mention two things again. So say M mod K was a symmetric space. So far we usually had G to be the full isometric group, which acts transitively. Right? And then we said that M is irreducible if K not acts irreducibly on say TPM if K is the isotopic group at P. Right? So if the identity component acts irreducible in tangent space, I call it irreducible, so that's my definition. And then we proved a theorem last time, a proposition. Maybe two things. One was that let's say if G mod K is a symmetric space, which is also simply connected, and the following things were true. First was that M is a product, M1 cross MK, where Mi are irreducible symmetric spaces. So at least if it's simply connected, I just split it into a remaining product of irreducible ones. And if M is integral-composable, or not a product, that implies it's irreducible. But the converse was not true because we had a counterexample. Later we're going to prove the following. I think I mentioned this a little bit, but let me make it specific. So if G mod K is symmetric, simply connected, this implies that M is Rn cross M prime, where Rn is a flat metric. And M prime is irreducible symmetric. Sorry. What am I trying to say? If M is irreducible symmetric, simply connected plus irreducible symmetric. n prime is irreducible and indecomposable. Okay. So remember, I said that Rn is an exception to the converse because Rn can be written as On cross translations divided by On, because this group acts irreducibly on the tangent space, so it's an irreducible symmetric space. But that's the only exception, in the sense that if it's simply connected, I can split off an Rn possibly. Whatever is left is indecomposable. So irreducible, indecomposable is the same thing except for this flat factor. This flat factor will always cause problems. But of course, it's uninteresting in a way, so I split it off anyway. So in that sense, it's not so bad. For example, another thing we're going to prove, so that's maybe part A. Part B will be that Pol P is equal to K. So remember, in general, we had the inclusion, that one is contained in the other. That's how we prove things like this here. But it doesn't say how big it is. In this case, it's trivial, Pol P. But if you're not in this case, so if you're splitting out your Euclidean factor, then they're actually the same. Okay. So we're going to see both of those later on. What else did we do? I think that was it. And I mentioned last time that we want to talk about the local theory now. Okay, so the local theorem was supposed to be the following. A M is locally symmetric. If known, if number R is equal to 0. But actually, I think I explained one direction. If M is locally symmetric plus simply connected, this implies M is symmetric. This kind of nice infinitesimal condition is actually equivalent to being symmetric if it's simply connected. Part C, which I'm going to use to prove part B, is the following. So if, let's say, M1, M2 are, let's see what formulation we want to formulate. Two symmetric spaces, simply connected. And I have a linear map from TP1M to TP2M, which is an isometry. So pick a base point in M1 and M2, and say I have a linear map from the tangent space to the tangent space. That's an isometry, such that L star R2 is equal to R1. So in the sense that if I take, say, R2 applied to L, U, LV, LW, that's L of R1 of UVW. So compatible in this sense, right? That's how we often write it. Putting back the curvature tensor at that point in M2 to M1 with this linear isometry here, I get the curvature at 1, or L respects the curvature in this sense. Then the conclusion is, then there exists a isometry F from M1 to M2 such that the derivative at P1 is equal to my given L. Okay. So part C is kind of a surprising fact. So of course, first notice that it's something you would expect, right? So if two things are isometric At one point they must agree, and the curvature must agree. If I have an isometry from one to the other, it must respect the curvature. Here I require this only at a single point. Right, so I pick a point here, pick a point here, and a linear isometry that respects the curvature extends to a global one. So it's kind of the analog of, say, what we did for Lie groups, that a Lie group is determined by its Lie algebra. Right, here I'm saying the symmetric space is determined by the tangent space at a point and the curvature tensor at a point. That determines the symmetric space completely. So it only depends on what happens at one point, just like for Lie groups. That then makes it believable that you can reduce the whole theory to some kind of linear algebra theory, which we're going to do a little bit later. So this here is certainly the very interesting part. We're going to use that to prove B. Part A is easier, though, so let me start with part A. So in this direction, we said, so to see that nabla R is 0, I observed that SP is an isometry. It respects curvature. And if I apply it to something of this form, this must be equal to, because it's an isometry, but here I have 4 arguments, so this is the same thing as R, nabla XR, Y, Z, W, and this is minus nabla XR, Y, Z, W. Because SP is minus identity at that point, right? So this implies nabla R is equal to 0. This was one direction. Also, to be precise, I want to show that this vanishes at a given point P, and then I use a symmetry at that point P to prove it's 0. Okay. And this was this general principle that if I have some tensor of odd order invariant under the isometry, invariant under SP, it must vanish. R has even order, nabla R has odd order. So this was the easy direction. So for the converse direction, so assume nabla R is equal to 0. And let's say fix a point P and a normal ball, some small radius epsilon around P. And then I have the exponential map from a small ball in the tangent space to the ball in the manifold. That's a diffeomorphism. And remember the symmetry at the point P applied to a geodesic was equal to exp P of minus TB. Right, so it reverses geodesics. So that's a well-defined map. Right, so this defines my map, SP from the normal ball to the normal ball. I need to show that's an isometry. Right. And then if I do, then my symmetry is a local isometry, and that's what it means to be locally symmetric. Right? So that's the goal, show that SP is an isometry. And for this, we just compare the exponential maps. So I think I mentioned this last thing. What I have to compute is I have to compute the derivative of xp at a vector v applied to w. And we said we do this using Jacobi fields. So let me recall a few things I mentioned last time. Elementary things about Jacobi fields. So gamma of t was a geodesic. And you say, and you take a one parameter family of geodesics. So geodesic for all S. And then I take the derivative of this curve gamma S of t with respect to S at S equal to 0. I call this J of t. This is a vector field along gamma. Right, so infinitesimal versions of a geodesic is a Jacobi field. So this is called a Jacobi field. And then one proves that equivalently this is given by a solution of the differential equation. For the vector field J along the geodesic. So where here my shorthand notation is that this is nabla gamma prime J Cohen derivative along the geodesic. Right. So one conversely look at solutions of a differential equation like this. It's linear, and then one can show that it's the derivative of one parameter family of geodesics. And then the claim is that the derivative of xp applied to V at the point V applied to W is J at 1, where J is a Jacobi field along XTV with, so now I have to write down initial conditions, the second order linear differential equation, so I have to write down the value and the derivative. That's equal to W. So this is the important statement of how to compute the derivative of the exponential up into the Jacobi fields. Like the proof is very easy. Someone remember what I do to prove this? I have to write down some kind of one parameter family of geodesics in order to get this formula. So how do I compute such a derivative? Right? I would take a curve through this point in this direction. Right? So what should I do then? I should take a curve through that point in that direction. So what curve should I take? Pardon? Can you write down a formula for me? A very simple one. So I want it to be a geodesic, so I put a t in front of it for the t parameter. And now the curve should depend on S. Should start with V and tangent vector W. Suppose they're in the tangent space. So I take V plus SW. Right, now when S equal to 0, I get V, and derivative is equal to W. So now the chain rule says that if I differentiate this here, I got a Jacobi field. And then you check the initial conditions that this is true and this is true. Okay. That's the proof. So very simple. Like one of my favorite questions when I do an oral exam geometry is prove to me with your bare hands that a flat metric is locally isometric to Rn. With your bare hands, not using any theorem. One has to understand how to compute the derivative exponential map. In that case, an isometry if the manifold is flat. Right? So one has to somehow recall this formula and see how to use it.
The question is to prove what?
That a manifold that's flat is locally isometric to Rn. Okay. Because if it's complete and everywhere flat, it's even isometric to all over N. In fact, even that's probably should be the question. I take take first a local question, show it's locally isometric to Rn. If it's complete and simply connected, show it's globally isometric to Rn. Right? That's something you can do with your bare hands if you understand what's going on. One of my favorite oral exam questions. Okay, so now we can use that. Let's see. Over here. So let's look at this Jacobi equation a little bit. And what we can that's my Jacobi equation. I want to make a statement about Jacobi fields, which is related to this kind of reflection of the geodesic at the origin. Right. So first, let's observe the following. Well, let's maybe first. Often, how one proves things about this differential equation is by choosing a parallel basis. Right. So I can choose a parallel basis. X1 of t up to xn of t along the geodesic. And this becomes a matrix differential equation. Right, so where the matrix is just R applied to vector V is R applied to V gamma prime, gamma prime. Okay. And then this is just a matrix equation, J double prime, plus R composed with J is equal to 0. So second order linear matrix differential equation. Okay. Of course, this here depends on T. The coefficient matrix also depends on T, which means you can't write down the solution explicitly. If it was constant, you can write them down. If they're not constant, you can't write them down, or at least you can say that solutions exist, and because the differential equation is linear, they're defined for all time. Right? Which is important in our formula because we have to go all the way up to 1 to be able to say this here. So I have to know they exist for all time. That's because it's linear. Okay. So now if it's a symmetric space, I can have a special property, namely, what does nabla R equal to 0 imply? That means that if X is parallel, then R of X gamma prime is parallel. Then that's what nabla R implies. More generally, say R is parallel if and only if X, Y, Z parallel imply R of X, Y, Z parallel. So I take parallel vector fields and parallel vector fields. In fact, you can regard that as a definition of being parallel if you want to, but it's easily to be equivalent. So in our case, gamma prime is a tangent vector of the geodesic. So that's parallel by the definition of a geodesic. So it takes X parallel to X parallel. So this matrix RT here has that property. The matrix RT is the matrix of R written down on a parallel basis. That means RT is constant. That's what this means for this kind of matrix differential equation. So that's what's special about symmetric spaces. But the Jacobi equation, this means that RT is constant. So my differential equation is one with constant coefficients. That's very special. Particularly if I want to, I could write down the solution explicitly in terms of some kind of matrix exponential, which at some point later on we may want to do. But right now, just observe the following consequence. If J of t is a solution, then J bar of t, which is J of minus t, is a solution. Right, because the differentiate twice, minus comes out twice, cancels, and R minus t is R plus t. Right, so just reflecting the Jacobi field gives me another Jacobi field. So, but of course, this J bar is now Jacobi around the reflected geodesic. Right. And that's all I need. So now let's compute this here. This is J of 1, where J at 0 was 0, and J prime at 0 was W. So J, then I had my Jacobi for J bar. So what does J bar satisfy? It's also 0 at 0, clearly. And now the coherent derivative for J prime at 0 is equal to minus J at 0. Because it's just differentiate use a chain rule here. So it means I would now take the lengths. That's the same thing as the length of J bar at 1. And that's the length of the X P V applied to X. So let's see. This gives me the derivative of the left-hand side. I want the derivative of the right-hand side. So that's the derivative at minus V applied to minus W. Okay. And that's, of course, this here is up to sign precise as J bar. J bar at 0 is 0, and J bar prime is W, is minus W. So actually they're the same. Okay. So that means this expression here has the same derivative as this expression.
To prove the quality of the norms of shape 1 and shape 2, you are using that the equation is the same because essentially it's linear.
This is true in a parallel basis. Right, so to say it's constant, I had to use a parallel basis. In that basis, it's a constant matrix differential equation. In that basis, meaning in that parallel basis, this and this is the same up to sign. When this is the same at x TV as this at x minus TV. Therefore, they have the same norm because it's the same in a parallel basis. Okay.
So it's meaning it's missing minus.
Well, taking an absolute value sign.
I mean, in front of the 1, J bar of minus 1.
Ah, yes, yes. Thank you. Thank you. Yes. Very good. That's where this minus comes from, I guess. Right. Thank you. That's the proof. Okay. I think a proof like this you also find something similar to this you find in Docamo. When Docamo proves that a space of constant curvature is isometric to your model, he uses precisely this kind of trick. But now, in addition, you can just explicitly write down what the solutions are for J. So even more than this, you just write down the solution and observe that if you have two spaces of the same constant curvature, the solutions are the same in a parallel basis. And then it's locally isometric to your model. So that's analogous to Docamo, but here I don't need constant curvature. Exactly what I need is this condition here. That's all I need. Constant curvature, of course, implies nabla r equal to 0. If r is constant, it's derivative 0. But that's all I need in the proof. So much bigger condition. Okay. And in fact, so the symmetry spaces are essentially the only spaces where I can solve this kind of differential equation explicitly. Right? If this is not constant, you can't write down solutions. If it's constant, you can write down solutions. Okay. So later on, we'll do that, write down explicitly what do the Jacobi fields look like in the symmetric space and derive consequence from that also. But right now, that's all we need. So part A is done. Now I'll do part C. And for this, I want to use what is sometimes called the Cartan-Ambrose-6 theorem. Which answers this kind of question: if I give you an isometry at a point, when can I extend it to a global isometry of the manifold? That's the kind of question that Cartan-Ambrose-6 answers for you. Certainly, you need something like this. It must respect curvature. That's in general not sufficient. So let's say N1 and 2 are complete. Let's say the second one is simply connected. And we pick 2 fixed points and an isometry L from TP1 to TP2. On the tangent spaces, such that. Another question is, what do I require? So certainly L star R2 is equal to R1. But now I need a stronger condition. And some of you may have seen that. What's a stronger condition than that? To get even just a local extension. I think that's called Cartan's theorem in D'Occamo. Which is what it proves that a constant curvature space is locally isometric to your model. Anyone remember what that says?
But essentially, didn't you ask that? Didn't you ask that L preserves the curvature approach?
At the point, yes. But clearly, that can't be enough in general. If number R is 0, that's good enough. In general, if I just know at one point the curvature is the same, how could that imply anything? That's not sufficient. So when can I extend it to say, an isometry of the normal ball? Say, when can I find such an F? It's clear what it should do, right? It should take X P1 TV to what? X P2 of TLV, right? Because an isometry, if it exists, must take geodesics to geodesics. That's what they look like in this normal ball here. And the initial vector of the geodesic is V, so it must be taken to LV. So I know what it looks like in a normal ball, the potential isometry. But the question, is it an isometry? Well, I claim I can now do the following. So I have my origin here, P1 goes to P2, right? If I take any geodesic, say gamma 1 over here, I have a corresponding geodesic gamma 2 over here, given by this formula, right? This is gamma 1, this is gamma 2.
Is the same rate?
Pardon?
It's the same epsilon on both sides.
If I want an isometry, sure. The epsilon is
Because, of course, the two inflows are complete, but are you taking totally geodesic ball?
I'm just here I'm assuming that they're normal balls, right? Which makes this map well defined. If this is not a normal ball, then this is not a one-to-one correspondence. If it's a normal ball, it is. And then V must be length less than epsilon. Right? Then each point in here is uniquely of this form. And conversely, that makes this into well-defined maps. So I have to choose normal balls of the same radius, certainly because an isometry preserves the radius. So I want the epsilon to be the same, and small enough so it's a normal ball. So what can I do now? I can take pair translation along gamma 1. I can take pair translation along gamma 2. So for each t, in fact. So I can go along this geodesic back to the origin. and use parallel translation. If I have an isometry, geodesics are taken geodesics, parallel translation must go to parallel translation, and curvature must go to curvature. So I require even stronger that gamma 1 star R2 is equal to P gamma R2 L of that, or L star of that, equals P, let's see, where's the 1, where's the 2? Let's think about that. So let me say it in word. I take my curvature tensor at some point to the normal ball. I take the unique geodesic to P1, parallel translate that tensor to that tangent space. Do the same thing over here at the corresponding point, and now compare it with the map L. Then it should be the same. So if I take the pullback of the second curvature tensor with gamma 2, it should be the pullback of the first curvature tensor with gamma 1. On B epsilon P1. Right. That's a strong condition in this. For every point, somehow the curvature compares in a natural way that one could think of if you have some kind of isometry. Right? This has to be true for an isometry. And this then implies, that's part A of Hamburg fix if you want to, this implies that F, so the above F, is an isometry. And that part you find, so this is part A of Cartan-Ambrose 6, that yet you find in Ducamo. I think it's called Cartan's theorem, he proves that. By the same kind of argument as we did over there, that you compute the derivative of the exponential map, right? That's how you compare these. You have to show they have the same norm, right? So you look at the Jacobi equation. Jacobi's equation is given by a curvature tensor, right down the parallel basis, because here I'm using parallel translation. And so then in that parallel basis, on the left and on the right, I get the same matrix differential equation. In general, now the coefficients won't be constant, but at least I get the same differential equation, and therefore this is an isometry. Now the global version of that is a little more subtle. That's the Ambrose-Hicks part. If gamma 1 in M1 is a piecewise geodesic, and gamma 2 the corresponding piecewise geodesic in M2, I'll say a minute what that means, then I need that, again, the same condition. L star P star gamma 2 of R2 equals P gamma 1 star of R1. Okay. So what does that mean? So I start with P1. So I know that close to P1 I take these unique geodesics, but to get anywhere else, I have to do the following, which is somewhat subtle. I'd have to take a piecewise geodesic, so I find in many points are certain breaks. Okay. So how do I now construct the corresponding picture along P2? Well, certainly the beginning part is clear. Right? This is a geodesic. I use that correspondence using the map L here, like I did here. There's a corresponding geodesic. I go to the corresponding distance. Right here, this is, say, time t. There's also time t. Now how do I continue? Well, I take this tangent vector at the break. I parallel translate back to P1. I go with L and parallel translate back over there. So I claim I get a corresponding vector here, which is a parallel translate of this break direction, if you want to. Now I go along that direction the same distance. Right? So if this is S here, I go distance S. The next vector is then obtained by taking this vector, parallel translate, go over pair translate, get a corresponding vector. Then I keep going like this. So if this is my gamma 1, I get a corresponding gamma 2 in a very natural way. Now this must also be true, right? Because a piecewise geodesic is taken to a piecewise geodesic with an isometry. Clearly, this is how the correspondence must be if the isometry exists, and this must also be true. And the conclusion is then there exists F from M1 to M2 such that the derivative of F at P1 is L. So it starts with the fixed isometry I prescribed, and it's an isometry in the sense that the length is preserved at every point. And F is a covering. In fact, this last property, that F is a covering, is an easy exercise from this condition right here. Again, a typical Duchamp exercise. You have two complete manifolds, and you have a local isometry between them. It must be a covering. Okay. Of course, if M2, did I assume M2 simply connected? I think so, right? They're simply connected, so this implies F is an isometry. But I only need the second one to simply connect if I want to, but that's not so relevant. So that's the statement of the cut on M6. Proof is in Giga-Ewing. The beginning starts just like here, the Duchamp, and now the question is, how do I continue? Right, some kind of piecewise continuation, using the same proof, kind of. And that's not so hard to do. I just keep going with normal balls from one point to another. And the question is, well, if I go from point P1 to another point in two different ways, and I do this kind of construction, how do I now get the same thing? And that's the heart of the proof, the difficulty of the proof. That's done one as some kind of what is usually called a monodromy argument. That if you go do two different ways in this kind of fashion, you end up with the same thing. So it's an outline of the proof. There's actually some open questions in this context. One thing you can ask, well, how many breaks do I need? Do I need breaks? Right? Why do I have to assume that G is a piecewise geodesic as opposed to just a geodesic? Isn't that good enough? And if I remember right, one can do it with one break, but it's not known whether you can do it without breaks. I think that's the story. I don't know. Yes? You can certainly connect any 2 points by a geodesic, absolutely. So the thing makes sense without any breaks. You might think it's true. I don't assume any breaks. The proof doesn't work. Let's put it that way. The proof doesn't work. The proof needs breaks. And it's kind of clear. If I look at this picture here, why do I need breaks? Well, I would want to go from P to Q, maybe using some geodesic. What do? I cover with finely normal balls. Then along these normal balls, I can go with piecewise geodesics. And I have to show that the map on the whole neighborhood is an isometry. The way that I do it is I go there and then I take a break. I go do the corresponding over here, I take a break. So this kind of monodromy argument works very nice as long as I allow myself to do breaks. If I want to go from here to here, if I do that with some geodesic, I don't know where it goes. It may not stay in this kind of continuation of normal balls. But if I allow myself to stay in normal balls, I can do it with a piecewise geodesic. That's kind of spiritually the reason why piecewise geodesics come up naturally in the proof itself. But whether it's true without that, I don't think is known. Giga-Eames proof doesn't show that it's okay with two breaks. I'm not sure why that's done. Then you have to work harder if you want to do it only with 2 breaks or 1 break. Anyway. So now we can prove part C. In fact, part C now becomes easy. In this theorem on symmetry spaces. Well, we know that nabla R2 is equal to nabla R1 is equal to 0. So all these pair translations is just equal to Ri at the point Pi. You always get back to the same thing. It's invariant on the pair translation. So all I need is this condition right here. Right? If I know this, then this also follows. For trivial reasons. Because everything is invariant on the pair translation. And then you use Cartan number 6. And then you're done. So then this isometry with this derivative. Right? In a way, so you might say, wow, this is an amazing theorem, must be very useful to show that 2 manifolds are isometric. Turns out to be completely useless. When could you ever compute all the geodesics in the first place, all the pair translations, and all the Gaussian tensors? If you do all that, you already know what the manifold is. Except for in the case where you always get the same thing. That's a symmetry space. So really, the only general application that this theorem has is this theorem from symmetry spaces.
The thesis is that F is an isometry, but from those normal balls?
Yes. And here, so part A is just F from the normal balls. So that's part A, right? That's the easy part if you want to. And that's done under Carmo. Part B is a hard part. And there I get an isometry from, where did I formulate it? Over there, from M, a global one. So part A is a local one, that's easy. Let's define the Carmo. Part B is a hard one, that's global. And then I have to use this kind of idea of some kind of monoidromy. Okay. So it proves part C, and now part B is also very easy. Simply say let L be equal to minus identity from TPM to TPM. And certainly L star of R is equal to R, because there are 4 arguments, right? Minus cancels. I get the same thing. So it satisfies this condition there. And this means the existence of the SP from M to M. Now symmetry, which has this as a derivative at the point P, and that's exactly my symmetry. Okay. Is there a comment?
The quantity of the arguments of the curvature tensor is convenient now.
Absolutely. It's crucial everywhere, right? It's crucial everywhere. We'll see more applications of that later on. But same kind of idea. Okay, so that proves this relationship between locally symmetric and globally symmetric. In the notes, you also find a proof. I'm not going to do that now. Not the consequence of this Cartan ambo 6. I guess that's the only other thing that I know it's useful for, that the group of all isometries fixed on your point is compact for Riemannian metric. But I mentioned that earlier. We've used it, I think, already once or twice. It's an important ingredient in proving that isometry group is a Lie group, that the isotropic group is compact. And that follows very easily from Cartan ambo 6. So you can read that in the notes. I'm going to update the notes later on. I made some improvements. Okay, next comes the very important idea, which is called Cartan involutions. So we already kind of saw, well, in fact, that's the statement right here, that being symmetric is an infinitesimal condition. Right? If I know the curvature at one point, I know the symmetric space. Can I formulate that in terms of the Lie groups? Right? M is G mod K. In terms of G and K, can I see when G mod K is a symmetric space? So that it really becomes completely a problem in terms of Lie groups. And that one can do. So first, observe the following. So we already knew that M was I of M mod K. I also claim it's equal to I0 of M mod mu K prime. So in other words, I0 of M acts transitively on M. There are two ways to see that. So we saw in the very beginning that I of M is transitive because symmetries take any point to any other point, right? But these kind of symmetries do not have to lie in the identity component. So it doesn't quite imply, that argument doesn't quite imply that I0 of M is transitive. But remember, we have transvections. T sub t, which takes gamma of 0 to gamma of t for any transvection along a geodesic. So I can go from any point to any other point with the geodesic, and then I have an isometry which takes that point to that point. And of course, transvections must lie in the identity component. So it's a one-parameter group. This implies that I0 is also transitive. There's also another general fact behind this, that if I have any homogeneous space, say if a group acts transitively on a space, then the identity component of the group also is transitive on the space. That's a completely general fact of homogeneous spaces. But there one has to think a little bit why that's true. Here it just follows from what we saw already. So we're often going to write now my symmetric space M as G mod K, where G is the identity component. And there are all kinds of reasons why that's a good idea to do. From now on, I'm going to assume that. And of course, K is isotope of some point P. So now I have the symmetry SP, so I fix a point P. I have the symmetry SP from M to M. Notice that SP may not lie in K, because K is now only the isotropy of the identity component of the manifold. Notice that K may not be connected. I'm not saying that K is connected, but I want G to be connected. Later on we'll see why that's useful. But nevertheless, SP induces an involution. What should I call it? I'm going to call it sigma P maybe? Yeah, sigma. Which depends on the point P, which is, so from G to G, which is conjugation. Because that's the same thing as SPG, SP inverse, because the inverse of the symmetry has derivative minus identity again at the point, and therefore it's just the symmetry itself. Okay. We induce involution on G such that the following holds: if G sigma is a set of points in the group which are fixed by sigma, then we have that G sigma 0 is contained in K, is contained in G sigma, which causes a subgroup G. And this is the important relationship. So notice here that this is a connected group. This may or may not have several components. We'll see some examples a little bit later that they certainly sometimes have several components. K is any group in between here and here, but it restricts K very much. Because, of course, this group and this group have the same Lie algebra. This means the Lie algebra K is determined just by the symmetry SP. Right? I'm fixing my symmetry SP, I conjugate with it. That gives me an automorphism of the group, and it has this property. Later on, we're going to see that there's a converse, that if I have an automorphism with this property, it gives me a symmetric space. So I can somehow characterize in a certain way symmetric spaces by these kind of what are called Cartan evolutions. So sigma is called a Cartan evolution. So Cartan, in fact, used those kind of involutions to classify symmetric spaces. That kind of now sounds believable, right, that I would classify symmetric spaces. Reduce it to the case where G is a simple Lie group. That's one of the first steps one does. We do that later on. If G is a simple Lie group, I have to classify automorphisms, involutive automorphisms. That's not so hard to do case by case, which is what Cartan did. And then one gets a complete list of all possible symmetric spaces. So that's makes these Cartan evolutions so important. But right now we're just going to do one direction, that a symmetric space implies the existence of such a Cartan evolution. Sigma certainly lies in out G, because it's conjugation by an element, conjugation automorphism. And sigma squared is out of SP squared, which is identity, because SP squared is identity. Because the derivative of SP squared is plus identity at P, and that makes it equal to identity globally. So the first part's easy, right? So this certainly implies an involutive automorphism. And I have to prove these two properties for the fixed point set of the automorphism. So let's see which one we do first. And then we do this inclusion second. So what does it say? So I take an element in K, because Kp is equal to P. Right, K was defined as the isotropic group of the point P. That's how it's characterized. Now I want to show that sigma K is equal to K, or that SPK, SP is equal to K, or that the commute if you want to. So any one of those is going to apply my claim. Let's see, maybe we'll do this one right here. They both are symmetries. And the fixed P. K fixed P by definition. SP does, K does, SP does. So they all take P to P. So what do I have to show? So that the derivatives are the same. Right? So what's the derivative of SPK, SP at the point P? Well, SP is minus identity, that's minus identity, they cancel. I get just the derivative of K at the point P. And so this implies now, because these have the same value at P and the same derivative at P, that they must be the same. And that shows that K lies in G sigma. So that's the first part. Second part says that identity component is contained in K. how do I prove things about connected groups? It's often very convenient to do it in neighborhood identity and then use a fact that generates the whole group. So let XTX be lie in G0 sigma. First, notice that certainly, say, G0 sigma is a Lie subgroup of G, since sigma is an automorphism. Right, if I take a product or two things that are fixed by sigma, the product is fixed by sigma. So it respects the group structure. Because it's defined by an equation, it's closed. So it's a closed subgroup of G, therefore it must be a Lie group. Right? So this thing is a Lie group. So I take a one-parameter group which generates the whole identity. And now I need to show, what do I need to show? That this lies in K. So I want to show XTX fixed at a point P. Using what? Using that it's fixed by sigma. Right, so I know that sigma x tx is equal to x dx. But what does that mean? What is sigma applied to one parameter group?
This is the exponential of the derivatives.
Right. This is x of t d sigma of x. So it must be x dx. That's not quite enough yet. Now I'm going to apply this to the point P. Of course, I want to show that's equal to P. What can I say about d sigma x? From this equation already. Let's see. These, of course, are both one-parameter groups. The initial condition is this. So this certainly applies that d sigma applied to x is equal to x. That makes this equation vacuous. Ah. Yes, we don't need this. Let's now look at
here we just use its automorphism.
right. I have to now use that. It's conjugation by the symmetry. I haven't used the symmetry yet. That's right.
You have to use it.
Yes. So what does this say then? So sigma is at SP. So I apply SP, so SP exp tx SP is equal to exp tx, right, because this is the sigma of exp tx. And now I apply to the point P. Okay. So this is an equation in the group, and now I apply that to the points in the manifold. So of course here I have SP, but SP applied to P is P. So that means that SP takes x dx times P is equal to x dx times P. Well, how can that be? So now here I have group elements such that, so let's write like this, SP applied to GP is GP. Calling this thing G here. So it's fixed by the symmetry. Right? This new point, G times the point P, is fixed by the symmetry around the point P. I also know that G is close to the identity. That's in the one parameter group. So it means that GP is near P, because G is close to the identity. Well, how can that be? Let's draw a picture. Our usual normal ball picture. So I have a normal ball here. I have a point P here. I have my symmetry, and here I have my point GP. SP fixes this point, it's supposed to fix to this one also. That can't be, because what is the symmetry to? It takes it over here. So that means it must all be equal to P. So this implies that SP of that XPX times P must be equal to P. So in other words, XPX lies in K. Okay, because these were the elements G that was near the point B, so GP must be equal to P. Right? That's what this implies here. And therefore XPX lies in K, so going back here, that's what I showed, right? Fix the point P. And now this implies that G0 sigma lies in K, because G0 sigma is connected and it's generated by these one parameter groups. So it's actually fairly easy. This relationship is fairly easy. And that's a crucial thing. Now I want to prove a converse. So what would the converse be? Take any automorphism of a Lie group G that's involutive. Then look at its fixed point set. Choose any group K, which could be this one, anything in between. So I have a certain number of choices. And then the space G mod K should be a symmetric space. Okay. For this, we need some background. But maybe before I do some background, let me give you some examples which show how easy this is going to be. This is going to be used once we have a converse. Maybe let's do our symmetric space Riemannian. And this was ON or SON divided by S of OK ON minus K. So I want to define automorphism from SON to SON such that this is a fixed point set or is contained in it. Right? So these are block embeddings. Right? So this was the form A, B, 0, 0, and that AB was equal to 1. So it lies in here. Right? So I have to find automorphism from SN to SN, which is involutive, but this is a fixed point set. But that's not hard to do. What's such an automorphism?
So evolutions.
Yes, so sigma of A is what? I claim adjoint, conjugate with what we call AKN minus K. So this is a block matrix. The identity minus identity, 0, 0. I claim the fixed point set of that sigma is precisely this group. Because what happens if I multiply this kind of diagonal matrix on the left and on the right? So if I have a matrix like this, what happens if I multiply with this on the left and on the right? On the left, minus identity, multiply on the left, which one's by minus 1? This one and this one. On the right, sorry. Oh, this one and this one. And here the last rows are multiplied by minus 1. If I do it from the right, the last columns are multiplied by minus 1, so they cancel here. So what this conjugation does is multiplies the off-diagonal entry by minus 1. That's all it does. So fixed point set is precisely these diagonal matrices. Right? So if I know a converse of this theorem, this will be my proof, my quick proof that this is a symmetric space. Of course, now notice that what is the identity component of the fixed point set? Well, this group has two components, precisely SOK, SON minus K. And then the quotient was the oriented Gauss-Magnum. This then will also imply that, so here I have two choices, right? K could be this group or this group. These are my two choices. This will then imply that there are no other subcovers of the Gauss-Magnum which are symmetric spaces. It's oriented, the unoriented one. If I want to divide by a group that's still a manifold, which one can do, it's not going to be a symmetric space. Right? So this here is a very strong and useful property. Maybe example 2. I'll do more examples next week. How about when G was a compact Lie group? That was with a bind-volumetric symmetric space, right? And SP of G as identity of G was G inverse. Right? That was the symmetry of this symmetric space at the identity. Because that's not automorphism, right? So how do I use that? Well, what I do is I write G as G cross G divided by diagonal G. And the automorphism sigma takes G comma H to H comma G, whose fixed point set is precisely diagonal G. Right? And remember how G cross G acted. It acted via left and right translations. And what does the symmetry do in my group itself? The inverse of that becomes left translation by H, right translation by G inverse. So it precisely flips the two. Okay, so that's consistent. So this is my automorphism that makes the compact Lie group into a symmetric space. Okay. Also, I'm not going to have enough time to do the inverse. Let me maybe just introduce one more idea, which is very easy to explain, but it's going to be important. Namely, one gets what's called a Cartan decomposition. of G. Maybe I claim G is equal to K direct sum P, where K is the +1 eigenspace of D sigma, and P the -1 eigenspace. And here, so my symmetric space is again G mod K. So here I'm making the statement, if you want to, that the Lie algebra of K is a +1 eigenspace of sigma. But after all, the group K was fixed by sigma. So certainly, take the derivative, it's going to fix the Lie algebra of K. So that's not the main point. I then choose P to be the -1 eigenspace. Since it's an evolution, it's a direct sum. I can always do that. Now I get the following relationships. That's certainly in K. That just means it's a subalgebra. Right? But then I also get that Kp is contained in P, and Pp is contained in K. And that's simply because D sigma is an automorphism, and now it's clear, right? This is a +1, sigma D sigma respects the Lie bracket. It must be again a +1 eigenspace. +1, -1, that must be a -1 eigenspace. That's in P. -1, -1 must be a +1 eigenspace, lies in K. Okay. And these are the important relationships on the Lie algebra level. And then we're going to show a converse. So conversely, star and 2 star defines a symmetric space. So again, one direction that a symmetric space has such a structure that's very easy. Follows from this because this was very easy. Right? But the converse we're going to have to work a little bit on, although it's not very hard either. And now I've really reduced the problem completely into a Lie algebra problem. Right? I have a Lie algebra G, I have a decomposition of these properties, that gives me symmetric space. And if the symmetric space is simply connected, I get a one-to-one correspondence. So in some books, you see this as a definition of a symmetric space. I think there's a very nice book by Borel on symmetric spaces. That's his definition. Then he derives everything algebraically. In Helgason also, he quickly converts symmetric spaces into this kind of algebraic object and then proves everything algebraically. For example, this decomposition that I discussed earlier, that every symmetric space is a Riemannian product of irreducible symmetric spaces. But geometrically, it was just a consequence of de Rham, which is something that every geometer or every mathematician should know, the general geometric result. Very basic, very important. So then it's an immediate consequence of that. In Helgason, it takes him 3 pages to prove, because it does it algebraically. So it's fairly nasty. And also, some of the facts about the holonomial group that I did already, which I'm going to do next, he also work hard at, because everything is defined algebraically, but not geometrically. You can't use anything geometric. So I will always use geometry as much as possible. In fact, I think I'm not going to use any more geometry than what I used already, because I used quite a bit, right? I used geodesics, curvature, Jacobi fields, the Rham theorem, Katon MO6. So I used quite a bit of geometry, but that gets you all the basics very quickly. And what we do from now on will be a combination of Lie group theory and algebraic theory. But all the examples are going to come out very quickly out of this characterization. So far I only did Grassmannians and compact Lie groups, all these other symmetric spaces like Lagrangian subspaces, complex structures, inner products, all the natural geometric objects that are symmetric spaces. Well, immediately out of this here, I just have to give you an involution sigma. That's all I have to do. Then I have a symmetric space. And the metric is essentially unique also. So everything follows very easily. Only thing I have to add here, it's not only quite that there must be an involutive automorphism with this property here, K must also be compact. Remember, I want a metric on the manifold, and for the manifold, the isotropy must be compact. So I would have to classify in involutive automorphisms where, say, the fixed point set is compact. Right? That would be the additional condition on the involutive automorphism. And then it's a symmetric space. Of course, if I give you an involutive automorphism, I can write down what G sigma looks like very easily and just see that it's compact. But that's the extra condition I need to construct my Riemannian metric. On this level here, then, it's less convenient to say what it means that K is compact. It's a little bit stronger than saying the Lie algebra is compact in the sense that we discussed earlier. Or quite equivalent to say that there exists some compact Lie group whose Lie algebra K is compact. But anyway, maybe next week I'll do the converse.